Welcome everyone. Today we'll be solving a problem from the AHSME competition, or the former AMC, and this is one of the harder problems from the 1981 exam, I believe. And today we'll be going through the solution, and in the meantime we'll learn a fundamental identity. So what does the problem say? We're given a constant beta that is between 0 and pi, and also for real numbers x, that x plus 1 over x equals 2 cosine of theta. And our problem is to evaluate x to the n plus 1 over x to the n, where n is an integer in terms of n and theta. So pause the video right now if you want to give it a try before I get into it. I think the best way to start is to very simply solve for x in terms of the constant theta, and then see what happens. So we can do that by the common denominator method. We can get here that x squared plus 1 over x is equal to 2 cosine of theta. And so if we multiply both sides by x, we get a quadratic, and also if we move over the x term on the right side to the left, we get a standard quadratic in x. And that will simply be x squared minus 2 cosine of theta x plus 1, which is equal to 0. And we can solve this just by plugging it into the quadratic formula. So we can get that x is equal to negative b plus or minus the square root of b squared, which is 4 cosine squared of theta, and then minus 4ac, which here is just 4. And all of this is divided by 2a, which is 2. We can clean up the square root by taking the perfect square of 4 outside and get that this is equal to 1/2 of 2 cosine theta again, plus or minus 2 times the square root of cosine squared of theta minus 1, like this. And now you can see the 2's simply cancel out with the division by 2. So this is equal to cosine of theta plus or minus the square root of cosine squared of theta minus 1. Now this, the thing inside the square root cosine squared of theta minus 1 does remind us of the Pythagorean identity, the sine squared of theta plus cosine squared of theta equals 1, right? So what is cosine squared of theta? Maybe we can write it in terms of sine. Well, if we reverse the signs here, we get that negative sine squared of theta minus cosine squared of theta equals minus 1. And so moving over cosine, we get that negative sine squared of theta equals to cosine squared of theta minus 1. So really what's inside the square root is the negative sine squared of theta. And the negative sine squared of theta, well, there's a bit of a problem. It's always negative, because sine squared is always positive, and we reverse it, we get something that's always negative. And it's inside of a square root. So something inside of a square root that's always negative, that's not going to give us a real answer. It's going to give us a complex answer. So here we have this is equal to cosine of theta plus or minus the negative sine squared of theta. And well, negative sine squared of theta, it's a negative. We can factor out the negative 1 and the square root and put in the imaginary unit, which is a bit of a strange thing to do, but maybe it's right that this answer is always going to be complex, not real. So this is just equal to cosine of theta plus or minus I times the square root of sine squared of theta, which is sine of theta. That is always positive in absolute value bars, but I didn't put the absolute value bars because theta is between 0 and pi. So this is our final solution to this quadratic. And this reminds us of a very fundamental identity in all of mathematics. Behold Euler's identity. E raised to the power of I times theta equals cosine of theta plus I sine of theta. A very beautiful identity relating trigonometry and the complex numbers. For those familiar with calculus, there is a very elegant proof, not very rigorous, of this identity using Taylor's series. So I've left one here on screen if you are interested. But to us, it is important to simply know it. From here, we can write a corollary of this identity by making the angle negative. We get also that e to the negative I theta equals, well, if the angle is negative, we can use the parity of sine and cosine. So this is just cosine of theta minus I sine of theta. And notice here, our x, what we got to be equal to this. This is simply equal to the Euler's identity in this exponential form. So e to the I theta or e to the minus I theta, like this. It's a bit unsettling that we have two values for x when we are only asked for one, but really it doesn't matter which x we plug in, this will be the same expression. Notice, if x is equal to, say, the first one, e to the I theta, then we get that x to the n plus 1 over x to the n is e to the I n theta, right, the properties of exponents, plus 1 over e to the I n theta. And remember, the reciprocal of an exponent is simply that base to the negative exponent. So this becomes e to the I n theta plus e to the minus I n theta. And again, if you plug in the negative, you'll get the exact same thing. If x is e to the negative I n theta, the same laws of exponents apply, and we get e to the negative I n theta plus 1 over e to the negative I n theta, which is just e to the negative I n theta plus e to the I n theta. And because addition is, what's the word, commutative, I think, then this is the same thing. So it doesn't matter which x we choose, they will be equal. So can we simplify these any further than their exponential form? Yes, we can. We can convert them to their trigonometric form and add them up. And notice what happens when we do that. For the first one here, for both of them, the angle is n theta, and it is negative, so we have cosine of n theta, and then minus I sine of n theta. And for the positive one that we are adding, the same thing, but the sign is flipped. So again, cosine of n theta plus I sine of n theta. And look at this, when we add them up, the cosines become twice, they become doubled, and the sines cancel each other out. So this becomes 2 cosines of n theta. And that is our answer. In fact, we just did it. We just raised both of them to the n, the reciprocal, we added them, and we have this answer. So that is it. We are done. X to the n plus 1 over x to the n equals 2 cosines of n theta. How cool is that? So I just solved this problem in a very typical Olympiad way. This is how I would normally do it on an Olympiad, where I first solve for x in terms of theta, then notice the identity pop out, and then get the results from there. But if your mind is set on complex numbers from the very beginning of this problem, there is a way you can do it in basically seconds. From the complex numbers and Euler's identity, we have a valid expression for cosine of theta, which is equal to this, which is basically the same thing we just did right here. E to the I theta plus e to the minus I theta divided by 2. And if you somehow decided to substitute this value of cosine theta into here, the 2's cancel out, and you get that x plus 1 over x equals e to the I theta plus 1 over e to the I theta. And from here, you instantly see that x has to be e to the I theta or its reciprocal. And from that, you get this result basically right away, just if you substitute the right expression for cosine. So this problem can be done definitely much faster than solving for a quadratic if you somehow remember this expression for cosine, but I don't think many will. So yep, that is it for today's video. Hope you learned something new or maybe refreshed on Euler's identity. And thank you all for watching. I will see you in the next video.